Hopefully we'll see it. Okay. So everyone now should see sort of this purple banner at the top that says something along the lines of you're being recorded, or this meeting is being recorded, or something like that. Okay. So I'm going to do that for every single lecture. If I forget to do that, please remind me, because if I don't press that button, then the infinite knowledge that I spew from my mouth will be lost forever. What a tragedy that would be. Okay. So, right. If I don't press the record button, it's not going to appear on YouTube later. So that's thing number one. Now, you all have the ability to stop the recording if you want, but it is very, very important that you do not stop the recording. So if you look at the little toolbar and you press the ellipsis, it should pop up with the ability for you to stop the recording. Okay? Please do not stop the recording. If you do, then I'm going to have to restart the recording if I even notice that the recording has stopped. And if I don't notice that the recording has stopped, then we just lose the material. Okay? So you do have the ability to stop the recording, but I ask that you please do not do that. Okay? Otherwise, I'm not going to have the material to post on YouTube, and if you missed a lecture, then you just won't be able to have it for future reference. Okay, so it's nice that you'll have some electronic storage. Now, I don't think that it's going to be available immediately, so it takes the Microsoft Teams application some time to render the video, usually 10-ish hours. So you probably won't see the video posted on YouTube under my channel for another 24 hours or so from when it was actually recorded. Okay, so so far so good. That's that. Next thing I want to talk about is the modified syllabus. So I did modify the syllabus for the course, and I uploaded the modified syllabus to Blackboard. So you should all have that available, and you should all see that. So I'm going to share my screen right now, and I'm going to pull up the new syllabus for the class. Okay. So different teachers are choosing to do different things with their classes. The way that I'm going to handle this is basically I'll say that week number 2 is lost to school closure, and we're going to push everything back 1 week and get rid of finals week. Okay, so what that means is you have no final for this class. All of the exams that you take for this class are going to just sort of be these exams that emphasize the most recent material. All right, so what that means for you is the first milestone that you come upon, or that you really, need to care about, is the first exam for the class, which is going to be 1 week from this Friday. It'll be April 3rd of next week, right? So next week, April 3rd, which is Friday, is your first exam. All right. Then you have a second exam, which is 3 weeks after that. Should be April 24th. And then in week 11, which normally would have been finals week, we'll still have our normal class meeting times, and you'll have one last exam that Thursday, May 21st. Okay, so that's kind of how the class is going to go. And because you no longer have a final, I have adjusted the grading for the class as well. All right, so the syllabus also contains a new grading scale, not the scale, but the structure, which looks like this. So your simulation projects, 20%. I will probably only have 2 of them this quarter instead of what I thought was going to be 3. It's just kind of the nature of the crazy world we're living in. And then each one of your in-class exams will be worth 20% each. I've also increased the homework grade up to 20%. So homework was worth less before. It's worth a little bit more now. And I will be making the homework, not extremely challenging, but more challenging than I probably normally would have. Okay, so there's that. Before I get off this topic of the syllabus, let's bring you guys back. All right, so before I get off the syllabus, do we have any questions? I'll just take a second and check the chat. Do we have any questions about schedule, exams, grading structure, things like that? I'll give you maybe 20 seconds or so to pop some stuff in the chat. I'll have my delicious coffee that keeps me awake. How do you guys like my Milwaukee flag? Pretty sweet, huh? I have yet to adopt that even. What are they doing? That thing is amazing. Just to make sure the exams are not cumulative. That is correct. The exams will not be cumulative, but the material builds as we go. So the material that we cover in the first couple of weeks of class is very important for the remainder of the class. So like I said, the first couple of weeks of this class are generally the most difficult, and it's just an unfortunate byproduct of the situation that we have to move to the online classes during what I think is maybe the most difficult portion of the class. But yes, the exams will emphasize the most material, but we'll have bits and pieces of previous material in each exam, if that makes sense. Hopefully that makes sense. Are you still planning on doing recessions before exams? Unknown. I will give review problems for sure, but reviews before exams, unknown. I was wondering what that flag was. Now you know. Milwaukee flag. Bam! All right. Do I drop the lowest homework? Incorrect. I will not be dropping any homeworks. How will things change if a student were to get sick? Yes, that's the next point of conversation. I have a list of things I want to discuss. Okay, so next thing, the virus. Yes, scary times. The virus is going to affect different people differently. Some people might get the virus. Some people might have a family member that gets the virus. There might be tangential things like you lost your job and now you don't have internet, or your parents lost their job and you don't know what you're going to do or something. I don't know. It's going to affect a lot of people in different ways, and probably ways I can't even anticipate. And as we move to this sort of like online venue, it becomes like really difficult for me to keep tabs on kind of the pulse of the class and like what's going on with the students. So it becomes even more important now than in the past of like constantly communicating with me. Okay, like if something is happening and you're being affected, like send me an email and tell me what's going on, or come to my office hours and we'll have a one-on-one video chat and maybe tell me what's going on, and we can come up with a compromise. Okay, like I'm trying to be reasonable here. I do still have to evaluate your ability to do general rigid body dynamics. You know, it's my job, and it's a hard job when I'm separated, from you guys digitally. But I'm going to try my best. Okay. Like I said, there's going to be hiccups, but stuff happens because of the virus, because of the economy, or whatever the case may be. I really will try the best I can to accommodate as much as I can. That's all I can really say. Okay. Mentioned it'll be open note exams. It'll be open note if we ever return to the classroom. I doubt we will return to the classroom. I am very doubtful that will happen. Okay. With that said, if we do return to the classroom, things will proceed as I normally would have done with our general classroom, meaning closed note exams, typical 50-minute exams, so on and so forth. Okay, like a typical exam setting. If you had me in the past, you know sort of how I run my exams. Give you an equation sheet and away you go. But I don't have the ability to police all of you in your homes. Okay, like I can ask you to point your laptop down at your work, but maybe you have your sister on another computer doing stuff behind it. Like, I don't know, right? So I'm just gonna say open everything. If that helps you, great. Take advantage of that, so on and so forth. If you want to use an integral solver online and punch stuff in, I got no problem with that. All right. Maybe your grades will be inflated in my class relative to your other performance, but whatever. It's one quarter, so be it. All right. I don't have the ability to police you, so it is what it is. All right. Anything else? Good question. Good question. Okay. I think that's it for things I wanted to address. I will be monitoring the chat as we go. But if there's no other real questions, then I'll start in on sort of a review of the material and then some introductory new material. Okay. So I'm going to share my screen with you, and I have a notepad that I will write upon as we go. I will tell you that my handwriting with the notepad is a little suspicious, let's just say. As we go through and as I work through it, my handwriting will get better, I promise. Okay, so I'm going to do my best to get the point across. I think it's legible as it is, and it will only improve with time as I get more comfortable. Okay? Is the homework due at the time of class or 11:59 each night? The homework is due at the beginning of the lecture period. So you must submit your homework electronically to me, my email, heart@msoe, by 3 p.m. on the day that it is due. So this Thursday, in my mailbox by 3 p.m., your homework. Capiche? Capiche. All right. Capish. All right, got it. Okay. So you should all now be able to see my notepad that I will be writing on during the lecture period. Okay? So I'm going to pull up the chat here and make sure that I've got the chat available in case people have questions. And then I'm going to turn to my notepad and write. So what's nice is I got this microphone, so it kind of follows my head around. So I don't really necessarily have to look at the laptop to pick up the microphone. Okay? So let's talk about where we were when we left off. So last we left off, which was about a week and a half ago, we had just finished an example problem of fixed axis rotation, rigid body motion. So let's quickly review the rigid body motion, and then we'll start in on some new material. Okay, so let's go through this. So let's say review, and of course it's already not working. Okay, here we go. So review. And to review, we had 3 different types of rigid body motion that we were going to discuss in this class. So 3 types of planar rigid body motion. Okay, number 1 was translation. All right. Okay, translation was just strict motion of the piece. Let's see if I can get something for an example. Okay, here's my calculator. This is my handy dandy example. Translation is all points on the object following parallel paths. So if we want to draw that using our little potato analogy, here's our potato. Here's point A. Here's point B. And this object is going to move in space to another location where all points on this object follow parallel paths. So A here, B has the same sort of relationship with A, and we're following along here. This is a rectilinear path. Doesn't necessarily have to be rectilinear. It could be curvilinear, but I'm drawing a rectilinear path here. Okay, so here we have A and B on parallel paths. Okay, so we went through some math here, and we did some derivation to show that if this is the case, then the velocity of A, which is some arbitrary point on the body, is equal to the velocity of B, which is some other arbitrary point on the body. So that sort of makes sense. If all points on the body are following parallel paths, then the distance which they covered in the same amount of time should be the same. That is the velocity. All right, how much distance did we cover in the same amount of time? All right, so the velocity of A equal to the velocity of B. And also, we take the derivative of that with respect to time and find that the acceleration of point A is also equal to the acceleration of point B. All right, sorry about my B, a little suspicious there. I will try to be better. Okay. So that is the first thing that we talked about, translation. Very simple. All points on the body have the same velocity and same acceleration. All right. Next, we had fixed axis rotation. And here, again, is our body. And now this body is going to be spinning about some axis. Let's label it as A prime. Ron Rogers. All right, A prime. Let's say that there is a point that lies on this axis, which in our original derivation we called point O. Sorry about that, point O. And we're interested in the velocity of some arbitrary point on the body. Let's call it point P. All right. The location of P relative to O, which lies on the axis of rotation, can be defined by the position vector R, or R bar, or the vector R. Remember that I draw the little dash over the top to denote vectors in this class. And let's say that there is some angular velocity of this particular body. That is, it is spinning about this axis with an angular velocity, and we label that angular velocity vector as omega. So it looks like a W, but, you know, we're fancy and we say omega, all right? I'm not fancy, but whoever decided that this was the letter for us is fancy, okay? Sometimes I'm fancy. Okay, so this is omega, all right? So given this angular velocity and the location of point P, we derived that generally the velocity of point P is going to be equal to the angular velocity vector, omega, crossed with the position vector defining P, which we just call this position vector R. All right, so we went through a long rigmarole with a bunch of, specifically laid out points and all that sort of derivation. We talked about cross product and how the resultant of a cross product is the magnitude of the vectors, sine of the angle between them, all that sort of good stuff. But the point of the matter is we landed on that the velocity of this particular point is omega cross R. All right. From there, we took the time derivative to figure out what the velocity or the acceleration of the velocity is. So after taking the time derivative, we came up with, using the chain rule, that the acceleration of point P is the angular acceleration alpha crossed with the position vector R. So this thing might not necessarily just have angular velocity, but it might also have angular acceleration, which I've now added to the picture on the right. Angular acceleration alpha plus the centripetal portion of the velocity, which is going to be here omega cross the velocity of P. All right, so we have this sort of two-part acceleration, where here this is tangential portion of the acceleration, and here this is centripetal. All right, one thing to note is that we can write the velocity of point P as omega cross R. So you may see the acceleration of point P written as the angular acceleration alpha crossed with the position vector R plus omega cross the velocity written in its original terms, omega cross R, where this might be segmented by parentheses. Okay? So that's sort of where we left off with translation, fixed axis rotation. All right, from there, we did a practice problem. So I'm going to pull up the lecture notes that we have for this class and share my screen and remind you that the practice problem that we did for this particular class looked something like this. So we had this T slider that was rotating about a fixed axis, which was defined by the rod ABC. So we looked at what was the velocity and the acceleration of point E on this T slider as it sort of revolved around this fixed axis ABC. So we did things like define the fixed axis of rotation using a unit vector lambda, which defined A, B, and C. Then we talked about how the velocity vector was defined from theta dot and theta double dot. And then we used the equations that we derived for fixed axis rotation to determine the velocity and acceleration of point E, given what we knew about the rotation rate and the increase in rotation rate, so theta dot and theta double dot, as this thing rotates around rod ABC. Okay, so that's about where we left off. Okay, so if you guys want to pick up with me, I'm going to pick up on the notes, which is this particular slide here, though I'm going to go back to the writing pad where I will utilize the notes to describe what I'm going to present through the PowerPoint slides. All right, so here we go. So you should all see the writing pad now. I just want to check in with you guys one more time, make sure that you can hear me. How is the writing pad? Can you see everything on the writing pad okay? Let me just get like a thumbs up or things look okay, things look terrible, you need to work on your handwriting, worst drawer ever, etc., etc. Everything is Gucci. I'm getting some thumbs up from Shayla. Nice. All right. So far, so good. The potato looks delicious. Maybe I'll have some French fries later. Who knows? Okay. All right. So far, so good. Thank you for giving me the feedback. Also, if you have more feedback about the lecture and you'd like to tell me by email later, I would appreciate any feedback. Okay. If not, I'm going to continue with new material. All right. So before we move on, I want to talk about some relationships between things you might have learned about linear velocity and linear acceleration in your particle dynamics class, and analogies between those linear motions and now what we have with angular motions. Okay, so the topic here will be relationships. Oh, geez, kinematic relationships for angular motion. All right. So when you were in your particle dynamics class, you had general relationships between position and acceleration and time and velocity. Okay? So generally things like the derivative of the position is the velocity. The derivative of the velocity is the acceleration, and so on and so forth. Okay? Or sorry, I think I had that backwards. The derivative of the acceleration is the velocity, and no, I had it right the first time. Okay. Sorry, it's been a long day. All right. But generally, for linear motion, you can write velocities and accelerations in rectangular components, right? It's usually easiest to describe the velocity vector in terms of the components that define that vector, okay? Generally for linear motion, you can write, yikes, velocity and acceleration in components. All right, the most common way that we separate acceleration velocity vectors or even position vectors is into rectangular components, x, y, and z. It's what we're all probably most familiar with. There are other coordinates and other coordinate systems you could write it in, like cylindrical components or spherical components, for instance. But here we're just going to mostly stick with rectangular components because it's what we all know and it's very familiar to us. Okay, so in rectangular components, yeah, I don't know why it does this, but every once in a while it just like stops working. Okay, it's like my pen ran out of ink, even though it's like electronic pen. So every once in a while, I just got to like close out this software and reopen. Okay, but it works fine when I turn it off and turn it back on. It's like the magical engineering fix, right? Okay, so in rectangular components, you might see the velocity as something like the velocity in x, I hat, plus velocity in y, j hat, plus velocity z, k hat. Okay, so this is separating the velocity vector into its components. Or for acceleration, you might see the acceleration is the acceleration in x, I hat, plus acceleration y, j hat, plus acceleration z, k hat. All right. So this is, again, writing those linear motion components in terms of their rectangular coordinate expressions. All right. So we have an angular analogy now that we have rigid bodies that have volume. When you had a particle before and you're talking about the angular velocity of a particle, doesn't really make a lot of sense. Okay, particles don't have angular velocity, angular acceleration because they have no volume. All right. But now that we have these rigid bodies, we can talk about their angular velocities and angular accelerations. And like you have the linear velocities and accelerations, we also have angular velocities and accelerations, which can be written in their components. All right. So similar. For angular velocities and accelerations. Namely that we might have angular velocity vector omega, which is omega x I hat plus omega y j hat plus omega z k hat. And we may have similar idea for the angular acceleration, where your angular acceleration might be defined in three-dimensional components as alpha x I hat plus alpha y j hat plus alpha z k hat. All right, so where we have broken the acceleration components, just like you do for position, where you define a point in space by like its x component, y component, z component. Like I got some point out in space here that's defined by 1, 2, 7. Okay, for instance, you can do the same thing with these angular velocities and angular accelerations. Now, you know from your particle dynamics classes that there generally is a relationship between velocity, acceleration, position, and time. So for linear motion, we have these kinematic relationships. That might look something like this. The acceleration, we know, is the derivative of the velocity. Okay, so the acceleration A is dv dt. Or if you wanted to write this in individual components, you might see something like dvx dt I hat plus dvy dt j hat plus dvz dt k hat. All right, man, I really got to work on my handwriting. I promise I'll get better. This is just, make do for now. I'll practice. All right, so acceleration is the derivative of the velocity. And we also know that we could make an angular analogy here. So this is the linear motion. We can make an angular analogy. That the angular acceleration alpha is the derivative of the angular velocity vector omega. All right. So in components, that might be something like dwx dt I hat plus dwy dt j hat plus d. I keep saying w, but I should be saying omega. Like I told you, I'm not fancy. All right. D omega z dt k hat. All right. So this is writing acceleration in terms of the derivatives of the individual components of the angular velocity. All right. So that's your angular analogy. You also have relationships between linear position and linear velocity. So you might have another linear analogy. That the velocity is the derivative of the position, right? So it might be something like dx dt I hat plus dy dt j hat plus dz dt k hat. That's your velocity vector, right? Then the angular analogy. This is going to look a little bit weird when I write this, but it's just kind of how it has to be, is that the angular velocity omega is the derivative of the angular position vector theta, so d theta vector dt, which is d theta x dt in the I hat plus d theta y dt j hat plus d theta z dt k hat. Okay, so there's some angular position, right? If you've got a coordinate system and you've got a body that's rotating in that coordinate system, you can define the angle of that location relative to some axis on your coordinate system, okay, by angles theta x, theta y, and theta z. So let's maybe expand on that. I'll draw a little picture here. Okay, so here's x, y, z. And maybe you've got some point out in space here, P, that's defined by position vector r. And you can define that point P not only by r bar, which would have components x, y, and z, but you also might define it by the angle between that vector and the relative axes of interest. Okay, so for instance, here this might be theta x. Here this is theta y, the angle between that vector and the y-axis. Here this is theta z. Okay, so together this might define the angular position vector theta vector. Okay, which just looks a little bit strange here. Now, what's nice is in this particular class, we're not really working in 3D. All right, in this class, sorry, I'll move up so if people were looking at drawing that figure or trying to draw it, I'll keep it in view. All right, in this class, we stick to 2D. Okay, so what that means is we can simplify things a little bit. All right, namely that the acceleration vector alpha is going to be defined only with the rotation about the z-axis. So for us, typically this might be something like alpha z k hat, or as I'll write it in this class, our angular acceleration vector will only really have one component, and that will be the component in k, this out of plane rotation. And so we might just write this as alpha k hat. All right. Similar for, so similarly, we might have angular velocity omega, which is defined only by omega z k hat in this class. Or you might see me write this as omega is simply omega k hat. Since there aren't really components in any other directions, we might just say that the scalar value is entirely in the k hat direction. Right? So what this leads to when we start doing the kinematic relationships, the derivatives, so on and so forth, is that we'll see the following relationships exist in this class only. So this is for 2D, which is planar rigid motion, which is what we're doing in this class. We have something like omega is omega k hat, which is simply the first derivative of the position angle theta with respect to time in k hat. All right. Similarly, the acceleration vector alpha is going to be alpha k hat, and this is going to be the first derivative of the angular velocity vector omega in k hat, and this is also the second derivative of the angular position theta. All right, so you will use relationships like these to execute problem number 3 on the homework. All right, so these kinematic relationships relating acceleration, velocity, position, and time that exists for your particle dynamics class in terms of linear motion, linear velocity, linear acceleration, so on and so forth. We have very similar analogies that exist for angular motion between angular acceleration, angular velocity, angular position, and time. Okay? All right. So I've been working in the notepad a little bit, talking a little bit. I just want to get one more thumbs up and make sure we're all good. No loss of connection, volume is okay, those sorts of things. Thumbs up. All right. Yeehaw. Yeehaw. And I got to say, it's like strange. In this, I'm like talking to myself, right? I'm like sitting in this room, I'm talking to myself. I mean, obviously you guys are all there with me, but it doesn't really, I mean, it's very strange. It doesn't feel like I'm with 30 other people, you know? It just feels like I'm a crazy person talking to the wall. Yeah. Would you scroll up slightly? I can scroll up slightly. Just a reminder, the lecture will be available on YouTube if you ended up like missing a little portion of it. Okay, just keep that in mind. All right, so we got about 10 minutes left. I'm going to start in on the new slide deck. Okay, so on Blackboard, you have lecture 2. So if you're following along with the PowerPoint slides, I'm going to start in on slide deck number 2. Okay, so let's go. All right, so we talked about 2 of the 3 types of motion for planar rigid bodies motion. First, translation. Velocities and accelerations all the same. Great. Second, rigid fixed axis rotation, where we're rotating about one particular point, and we came up with the math there. Great. The third type, and what you're going to see 99% of the time in this class, is general rigid body motion. Okay? So general plane motion, I'll call it. And I'll call it plane motion because, again, in this class, we tend to stick to 2-dimensional objects, okay? Things that I can draw on this particular 2-dimensional whiteboard pad thingy, mabobber doodle. Okay, good. All right, so general plane motion. Let's motivate this by actually drawing what general plane motion might look like, and then I'll sort of break it down into individual components, okay? So let's consider a body with points A1 and B1 moving in a general manner to A2 and B2. All right. So I'm going to draw another potato here, and we'll talk through it. All right, so here's my terrible. All right, here's my rigid body. So my potato, it's got points on it A, 1, and here, B1. And we're going to move this body from its current location to another location, and it's going to stay in the plane as it moves, but it might have some rotation to it, okay? So it's not strictly translating, it's not strictly rotating, it has some general motion, okay? So later on it might have this kind of motion, where here we have over here A2, that's where I've moved to, and now I've moved over here, since it's kind of got like this rotation now, to B2, all right? So I previously mentioned that this general motion, as the object moves from location 1 to location 2, is consistent of both a translational and a fixed axis rotation component, okay? So consists of translation and fixed axis rotation. So let me explain that a little bit if I can. Let's assume that this body, as A1 goes to A2, it translated along a linear path. So let's assume translation of A1 to A2. That is this general motion as I go from A1 to A2. So here's translation. All right, so I'm assuming that I've translated my body from its position at A1, B1 to some other location, B2, like A2, let's call it. So if I translate my object from its position A1, B1 over to that location A2, I can think about what would happen for point B1 if it translated along that exact same path. Okay, so if we assume translation of A1 to A2, then B1 to B2 is a combination of the translation and a fixed axis rotation. Let me espouse on this just a little bit. All right, so when A1 translates from A1 to A2, B1, we might think about it also translating in that similar manner. From B1 to the exact same parallel path, and it's going to come to a point of about right here. All right, so there's this intermediate location that exists from the translation of A1 to A2 in the same translation of B1 to, let's call this point here B1 prime. Okay, and so this is same translation as A1 to A2. All right, but we haven't really gotten to our final location, right? We just at this intermediate location that is B1 prime, right? So we have this translational component getting from B1 to B1 prime, but now we need an additional rotation of our object. So our object, as it goes to its intermediate state, might look something like this, okay? And now we need an additional translation, or sorry, an additional fixed axis rotation to get us from B1 prime to B2. So the additional motion that we need is a fixed axis rotation of point B about point A2. So we need translation plus rotation of B about A. So there's this combination of the object translating. Here's my awesome NASA calculator. So it translates, and then it has to rotate to get into position. Okay, so that's what we're trying to draw here. All objects moving along parallel paths, translating together until point A1 arrives at A2, and then B1 prime pivots around A2 until it locates itself into location B2. So that's how we kind of think about this general motion. It's this combination of both translation and fixed axis rotation to get into position. Now, it might not necessarily have happened that way. It's very rare to see an object move in pure translation and then pure fixed axis rotation. But that's how we sort of think about it mathematically. Okay, so mathematically, this is the velocity of point B is the velocity of point A, the translational velocity of that particular point. It matches that, plus whatever velocity is associated with the fixed axis rotation of B about A. So that is the velocity of point B relative to point A. Okay, so it translated together, and then there was some additional velocity of B relative to A that was required. All right, you might also see this as the velocity of point B is the velocity of A plus the angular velocity of the body crossed with the position vector locating B from A. This idea that we have a translational component, and we also have a fixed axis rotation component. Okay, so we can consider the velocity of point B as a combination of both the translational velocity of A and the velocity associated with the point rotating into its position relative to A. Okay, so this equation here you will write a bazillion times in this class. This one you want to commit to memory. All right. Okay, so that'll do it for time for today. We'll dive in on this a little bit more next time. We have about a minute left. I just want to open the chat again one more time just to get some communication about how did it go? How was the pace? Was it too fast, too slow? Are you able to hear me during the process? How's the writing? Those sorts of things. So any comments you want to make would be appreciated. Otherwise, if there are no comments, feel free to leave the meeting. I'll post the recording onto YouTube and invite you to follow my channel on YouTube to get the lectures. Okay? Okay, great. No questions, then thanks a lot for coming. I'll stick around. Hey, best lecture so far. Wow, is this the first one that you've had? Just donated $2. Yeah, okay, I wish. I need to have like one of those little things that pops up on the screen when people make donations or like subscribe. It's like pring. Where's the pooch? Oh, he's at daycare today. The daycare's still open, so. I appreciate that comment, David. Thank you. One of these days I'll get the pooch on here. I'll introduce you guys. All right. Well, if you have comments or questions or concerns, please make sure to email me and we'll work it out. Otherwise, see you guys tomorrow. It's better than Swedish yelling at their microphone. Okay, well, I'm glad that I'm better than an 80-year-old man with technology. Okay. Thanks, guys. See you later.